So what we learned yesterday was that each instance weight are different from the original weights. And these weights are initially set to 1 by m. We train a predictor as in whether it could be regressor or it could be classifier. All right. And then we compute the weighted error. Okay. The weighted error is number of instances that are classified as correctly. The predicted class. Okay. So this is basically for the cases where the predicted class is not same as actual class. So the error rate is number of classes, number of labels, or you can say that number of y's, the predicted labels, is not equal to the actual label. Okay, so imagine that there was an algorithm which out of 10 instances, how many w's will be there? Total number of w's will be equal to number of instances. Out of 10 instances, its predictions were right 7 times. So what will be R in this case? The predictions were right 7 out of 10. So what will be R? Now, R is a error rate and predictions were right 7 times. So the number of times it made a mistake is 3, correct? So it'll be 3 by 10. Nikita, Prashant, Robert, Robin, and Satyajit. So the error rate is 3 by 10. So that's what we do here. And then what we do is we compute the predictor rate. This is the quality of how good is the prediction, right? How good is the prediction? And this prediction is basically the prediction is inversely proportional to the R. You can just give it a try. You can just give it a try and see what happens in case of all right, let's just say that this is my alpha and eta is 1. Let's say eta is 1 and we are saying log of 1 minus R by R, right? So in case, let's say R is 0.3, so it's going to be log of 0.7 by 0.3, right? And in case, let's say, what if the R is 0.7, right? In that case, it's going to be log of 3 by 7, right? So as error rate increases, alpha decreases, right? As error rate increases, alpha decreases, correct? So this one is big. So alpha for this alpha 1 and alpha 2. So alpha 1 is bigger or alpha 2 is bigger? Alpha 1 is bigger. That's right. So basically the predictor's weight we compute based on the error rate, right? So the one that's more accurate is going to have better alpha than the another, correct? Now, so if it's guessing randomly, R is going to be 0.5 and this is going to be 1, and therefore alpha is going to be 0. However, if it is most often wrong, right, the weight will be negative, right? If you can see that if R is 0.7, which is most often wrong, right? 70% times it was wrong. Therefore, it's going to be log of 3 by 7, which is less than 1. Therefore, it's going to be negative, right? This is going to be positive. All right. So not a big deal. It's just a simple relation between R and alpha. There could be many such relationships that you could also come up with. right, which have a similar behavior, and then you can observe which kind of thing is giving better outcome, right? Now, what we do at each progressive step, the weights that we calculated in the beginning, we update those weights. Okay, we update those weights, right? So we compute the here instead of rewarding the each of the predictor based on just usual accuracy, the definition of accuracy is changing. The definition of error is changing, meaning the instances that are left out, right? So you can see that the weights are going to increase. The weights are going to increase in the cases where the predictions were wrong. Okay, so the next one, that next predictor that we are picking up, for that weights are going to be this, and the error rate and the alpha is going to be computed based on these new weights. Okay, so instead of saying that every time imagine that we did not have this in place, right? So what would be the difference? The difference would be that we would be rewarding each of the predictors irrespective of the instances. We'll be rewarding or punishing or valuing each of the predictors equally. I mean, irrespective of which instance is it, right? That's the way we generally calculate the precision, the recall rate, and that's how we generally calculate the accuracy, that each instance has got equal value. But here, what we do is progressively we give more weightages to certain instances, specifically the instances that were where the mistake would happen more. Okay, and based on that calculation, we mark whether a predictor is important or not important. So what's happening here is the training of these algorithms and predictors is happening as usual, and training of these algorithms are happening as usual, just that their value, whose opinion matters most, is happening based on how many instances they are leaving, and are they leaving the important instances, or are they leaving the not so important instances. Okay, question from Deepak is, weight is more for error makers. That's right. Weight is more for the instances which made error, which on which the error was made. Okay, so you can see that what we are doing is, for the cases where the predicted value is equal to the same, the weight remains as such, while for the cases where predicted value was not same as the actual value, right? For those cases, what we do is we multiply it with the alpha. Okay, so since the e to the power alpha, because alpha might become negative or positive, right? So in case, generally the alpha is going to be better than 0, right? Because most of the predictors will have the accuracy a little above random, right? In those cases, what we do is we multiply the with a positive number. This is a positive number, okay, and so on, right? In the cases, the previous step, in case of previous step, the predictor did really bad, the accuracy went really bad. in those cases it'll become decimal, right? Which means that the previous predictor was really not doing well. Okay. Now these weights that you see here is basically used for computation of error rate of the next predictor. And then based on the next predictor, what we do is we compute the strength of each predictor. And based on that, once we are done with everything, then we keep on repeating the whole process over and over again. And once we are done, then we will do the prediction. We'll ask all the predictors to predict, okay? So once everything is done, the training phase is done, we can compute the predictions of all the predictors after, let's say we want to see whether a particular thing is spam or not a spam. We'll ask all the predictors. And since we know their strength, since we know each one's alpha, we can take their opinion based on that alpha, right? So instead of having a kind of a democracy, here we are taking the inputs from all the predictors and keeping in mind their alphas, right? All right. So Deepak's question is how the weights taken care by the next predictor. All right. So there are two very key aspects to it. Okay, let me just try. Okay, very key aspects to it. So, all right, let me say that there was an instance, and this. Okay, so what we did was we basically did a usual training and we asked them to do the prediction. Okay. Okay. And we noticed that for this case, yeah, no, we just give one predictor at a time. This is first predictor. Okay. So this is not for all, but for only one predictor. So we got correct results. Okay. And then we got wrong results. Then we got wrong results. And then we got correct results, right? So R is going to be, say, 0.5 and alpha is going to be 0, right? R is going to be how much? 0.5 and alpha is going to be 0. Now the weights, okay? Now what happened was we did not increase the weight as such because we know that e to the power of 0 is 1. So the weights of each one remain same. Can I do something else? Okay, let me just try doing adding one more instance. And yeah, right? So the mistake was, how much was the mistake? R is 2 by 5, which is 0.4, correct? R is 0.4. And alpha would be somewhere a positive number, right? This will be log of 3 by 2, right? Some positive number. So this is the alpha of this particular predictor, the previous one. Okay. Now what we do is we basically have a different set of weights. Okay. This one, now the weights we are calculating parallelly. Okay. Now when, let's say, we calculated some weights and the weights for this is going to remain as such. So initially, how much was the weight for each? It was 0.2, 0.2, 0.2, 0.2, and 0.2. Correct? These are the weights. Now, what we do is in the next step, here there is, let's say, another predictor. Okay, we're going to feed these. But before feeding these, we know that the weights are now different, but the training will happen usual, the way the training happens, and the same data going to be fed here. Okay, going to be fed here. Whatever data was there in the previous step, we're going to feed here. Now we got the prediction. Let's say this guy made the same mistake, this guy made the same mistake, and this guy made the same mistake, okay? And exactly the same way, okay? Now what's happening is that he did not really improve upon the accuracy. Now what will happen in this case? Now since the weights have been multiplied, then now the weights are, this one remains as 0.2, 0.2, 0.2 into e to the power, let's say log of 1.5. Can you tell me how much is this? It should be 1.5, right? You can see the alpha. Alpha is 1.5, log of 1.5 earlier, and then we are doing the log of it. Sorry, we are putting e to the power this. So it should be 0.5 multiplied by 1.5, correct? Similarly, in this case also, it will be 0.5 multiplied by 1.5. And then again 0.5, again 0.5. Now you see, notice this here. Now, how much will the R be this time? How much will the R be? Earlier we calculated R based on how many instances are wrong. This is wrong, this is wrong, right? So the R is going to be this time, okay, into 2 divided by, what is the total? Total is 0.2 plus 0.2 plus 0.2, right? And right, so 0.6 plus, right, 0.3 plus 0.3, okay. So how much is it? So now the R, you can see the error rate is bigger than 0.4, right? Let's just see that. 0.6 divided by 0.6 plus 0.6, right? Okay, so what we see here is that if the algorithm is same on which we are training progressively, we are penalized. We are saying that this algorithm, which has been basically trained on the same data, but the error rate is now more. Okay, his error rate is more. Therefore, we will rely on his opinion more than his opinion. This algorithm has more opinion than this, though algorithms are same. But since in the progression, what has happened is that since this one did not really, since this one did not improve upon the errors made by the first one, therefore those weightages went up and the error rate went up from 0.4 to 0.5. All right. Question is, how did we come to 1.5? Why did we multiply by 1.5? So here, what was the R? 0.5, 0.4, correct? This we agree. 2 by 5 is the 0.4. So, and what will that become? Log of 0.6 divided by 0.4, right? That is log of 1.5, right? And then the amount of weight that we multiply with is, so if R is 0.4, it'll become 6 by 4, which is log of 1.5, and eta is, for now we are keeping as 1, so alpha is log of 1.5, right? And then we are saying e to the power log of 1.5, which is actually 1.5, right? Yeah. Okay. So I hope you got the idea clear that we subsequently keep on penalizing. A question from Robert is, what methods would you use if AdaBoost underfits or overfits the training data? All right. Question is, what methods would we use if AdaBoost underfits or overfits the training data? So here we let it underfit or overfit. Okay, each individual subsequent trainer, subsequent instance, and right. So the way since we are applying multiple chain of error boost, multiple chain of predictors, the the chance of it is going to be basically it might start overfitting, right? So probably one of the ways of controlling the overfitting or underfitting is the learning rate called eta. If we increase eta, it's going to basically subsequently um, give more and more value to a particular algorithm which is doing better than the others, and so on, right? So so one thing we can control is the eta, the hyperparameter which represents the learning curve. And what else can we do here? All right, let's take a look. All right. So since we are having this as, a chain of multiple predictors, these predictors basically are going to be little diverse in the sense that they are going to be probably having the shuffle data. They are going to probably, uh, I think they do more. Here the point that I'm trying to say is how would we how would we ensure that our algorithms don't overfit, right? And right. All right. So so one hyperparameter is the eta that is changing, while the algorithms that we are going to use, let's say we use decision tree or others, those hyperparameters will remain as such. We can control those hyperparameters. We can set like how many leaves to go to, and should it pick randomly some features or not, and so on. Okay, increasing estimators, yes, that's another hyperparameters. Thank you for that. So here, specific to AdaBoost, what all we can do, we can change eta, that is one. Second is increasing or decreasing number of estimators or number of predictors, that is second. The third one was remaining parameters of individual what do you say, individual estimators remain as such. So those are the various hyperparameters you can you can basically fine tune in order to get better results from AdaBoost. All right, so let's move ahead here. This is okay, and but I think I would pay more attention to XGBoost. All right, because AdaBoost is more or less kind of kept aside for the reasons like we could not parallelize it, though it did better than normal random forest, but most of the work has been moved to XGBoost. Although random forest was also really highly performant in the sense that we could parallelize it, but but since I want to give you an overview of the algorithm, that's why we went into this. All right, so let's move ahead. And okay, so usually the most of the work is done under the hood, so you don't really need to know. Most of it is taken care by scikit-learn, and there are two versions to it. One is the real version, as in the version in which we do the real value calculation, and the other one is the integer calculation. All right, now moving ahead. So okay, So this is an example of how we are calling it. Here we are basically calling the Erebus classifier. We are passing our object of the classifier here. We are specifying the attribute like max depth. And then we are saying number of estimators is 200 and the algorithm is this and learning rate is 0.5. Even if you don't specify this, it'll work out well. Just that since we want since our outcome is basically based on, okay, this one is probably the soft voting one. Okay. Okay. So in case the model that you're using here, this one, in case it has a predict prob A, meaning if it can give the probabilities, then the algorithm that is automatically used is sam.r, right? Because here, since you're getting the probabilities, therefore the way it's going to calculate the last step in which it's going to, during prediction time, it's going to use the probabilities, the soft voting instead of hard voting, right? And in case the model that you're passing in the first argument is returning the integer value, in that case, it will be sam without r, meaning this formula that you see here, right? Here we are not taking into consideration the soft voting. It's basically the hard voting, meaning we ask all the predictors, okay? We ask all the predictors. We see the number of votes of each predictor, with keeping in mind the alpha of each one, and that's how we decide that which class to predict. Okay, while in case of real, what we do is we multiply the probabilities predicted by each one with alpha of each predictor, and based on that we sum up all the probabilities of classes and then say that this class seems to get most votes. Okay, so that's what is happening here, and that's the main variant between these two parts. Okay, and this generally switches by itself based on if the underlying classifier has prob A method or not. Okay, so all right. Okay, so if your Erebus ensemble, as we just discussed, is overfitting the training set, you can try reducing the number of estimators, or more strongly, regularizing the base estimator, right? As I was saying, base estimator, as in whatever you're passing here, you can regularize it a bit. So the tendency is that we make the decision tree a little bit more more stump, as in the depth would be lower. So here we are just made it really smaller, really smaller. Okay, and then we let it be there. Okay, so one way to think of most of not at a boost in general, but in general, the way we can think of ensemble is this, that probably would make more sense. I'll just give you an example. Okay, we call it, say, sorting machine. Okay, Galton board. All right, can you see my screen, the video? Right, you see this one, right? I'll pause it here. It's a really cool thing. I was observing it, and if you look at it closely, it's basically a chain of classifiers. Right? It's a sequence of classifiers. So let's say we are basically putting the small balls, and each small ball has a tiny bit of difference in their weight or density or maybe smoothness. And so these classifiers that you see is only like, like a decision tree. It's basically decision tree of one depth. It's breaking on some criteria. And as you do this, you see there's so many classifiers chained up. that the output of one is going to the next, and once we have, okay, I mean, this is prediction happening, not the training. So this is the prediction time. We're assuming that these are trained and they know how to divide. Now, you can see. So even a very, in ensembling, when we are chaining up many classifiers, even if these are really dumb classifier, but if you chain them, they should be able to do a lot of work. Okay. All right. This is not specific to the Ada Boost, but this is general with ensembling. Do you see the difference? So here the classification is bad, a little bit worse, and so on. Okay. And there are more practical examples also whereby there is not this one. Okay. Ensemble, not the Galton board. I hope everybody got the idea. What does it mean by ensembling in real life? All right, not this one. Okay. All right, I think.
Now get Wi-Fi at your home at an unbelievable price.
Just
with amazing benefits like router and no extra.
All right, so you can see this. Okay. No. Not really. All right. So I think the previous example was good. I've shared that. Okay. So basically, the ensembling is essentially a great technique, and this the Galton board video that I shared would give you a better idea that even really dumb classifiers should be able to classify if they are chained in a sequence. Okay. Question from Robert is, are you limited to the number of predictors that you can use with an Ada Boost classifier? So basically the answer is no, that we can do, in case of the Ada Boost classifier, we could use any base algorithm, right? We could either use decision tree, SVM, linear regressor, or anything that we would like to use. We can use any here. If we are using Ada Boost regressor, right, we'll be using the regressor here. If we are using classifier, we'll be using the classifiers here. So we are not really limited here, because the only difference is in case the underlying algorithm is giving probabilities, then we get the soft voting at the end of it, meaning it will use a different algorithm called sem.r. In case this does not give the probability methods, meaning it doesn't give the probability, it just says yes or no, in that case, we will be using a little different version. I mean, this will be using automatically. Okay. All right. A question from Robert is, can you use the same classifier with different hyperparameters? No. So at least this library does not allow us, but if we, I mean, the way the algorithm is working happens that we don't change the hyperparameters. Okay, but I'm not sure if there is another way. I've not seen the arrangement in the API where progressively we could have different set of classifier with different set of hyperparameters. Okay, So if you take a look at the API, the scikit-learn, and we say add a boost, classifier regression, in both the cases, the same thing. All right. So this is the base estimator, number of estimators, learning rate, algorithm, and random state. That shows that whatever object we pass, it will basically keep on cloning it, keep on retraining it. Okay. All right. So yes. So the algorithm as such does not allow us, but if we want, we can have our own variant from bottom up if we want to redesign it, and so on. All right, very good questions. Now moving ahead, and so just like add a boost, gradient boosting works by sequentially adding predictors to an ensemble, each one correcting its predecessors, meaning if the successor is correcting the previous one, we get it score, otherwise we don't give it a score. So we value only the successors which correct the previous ones. Okay, and in case it's not improving, it's keeping the same, we don't give it the score. So but instead of tweaking the instance weights for every iteration like Boost does, okay, yeah, great. A question from Manoj is, in Ensemble, we can use multiple classifiers to get the best results? Yes. In AdaBoost, we can use only one, but many times in series. So which method is better, right? There is no straight answer to it. There's no straight answer to it. Historically, using just the normal voting classifier is not as great as using AdaBoost, but you should always give it a simple try. Okay. All right. Now, there is another thing called gradient boosting. Okay. So gradient boosting works by sequentially adding predictors to an ensemble, right? Each one, this is what we just learned. In case of gradient boosting, instead of tweaking the instance weights at every iteration, just like AdaBoost does, this method tries to fit the new predictor to the residuals errors. Okay, so gradient boosting is basically proper chaining things. So far, in case of AdaBoost, we did not really chain it much. We were basically figuring out, the only thing that we were figuring out of all of this is who has got more alpha, right? Who has got which predictor is better, that's all. But in gradient boosting, we recompute the target value. We basically try to fit the new predictor on residual errors made by the previous predictor. This is very important point, and that differentiates the AdaBoost from gradient boosting. Let us understand how gradient boosting works by using decision trees as the basic predictor. Okay, so here are the steps we will do. First, we will fit a decision tree regressor to the training set. Next, we will train a decision tree regressor on the residual error made by the first predictor. Okay, these are this is how it works. So first of all, we fit the decision tree regressor to the training set. Okay, let's say we are the base algorithm that we are using in case of gradient boosting is decision tree, and gradient boosting generally works great with the regressors, as in when you do regression, then only you can compute the residual errors, right? So in case of gradient boosting, what we do is we take a base algorithm, train it, see the outcome, then see how much error did we get, Then on these errors, we train the next predictor, and then it does some errors, and then the next one is trained on the errors of the third one. So errors keep diminishing, and so on. Okay, so all right, and once we have done it, what we'll do is we'll ensemble. We will have like full ensemble, and then we can make new predictions using this. Okay, and we'll basically we will basically make the predictions on new instance by simply adding up the predictions of all the trees, right? So first one making some prediction, second one making some prediction. We add it because the errors will be basically minimized. Okay, so let's just take a look at it. So we'll generate some noisy quadratic training data. This is a quadratic data. So here you can see we are generating some x. This is some x values, and then y is 3x square plus some random values. Okay, now so first we will generate a decision tree regressor to the training set. Okay, so first we are doing the usual fitting. We are importing decision tree regressor, and we are doing the fit, and we are doing the second one. All right, so I'm trying to show you how it happens. So let's say first of all we use the decision tree regressor with a depth of 2, and we trained it on this data, right? We trained it on this data. This got trained. Once we are done with the training, what we do is we compute the next level of y's by subtracting the actual value with the predicted values. Okay, so whatever we trained this decision tree on, we are now doing the prediction. Okay, same training data, and once we have done the prediction, we are subtracting this. We are subtracting it here, and this is a new value. Now for the next step, the x remains as such and the y becomes y2. Do you see that? Is it clear to everyone? Okay, so I think in the chain of things we should have taught gradient boosting first. Okay, because this one is a real chaining. So yes, Deepak, Jainan, Manoj, Nikita, Prashant, Robert, Robin, and Satyajit. So I hope this is very clear. So first we generated some data, x and y equals 3x square plus some random values we are adding just to add noise. And this is the noise, this is the actual data. So random doesn't mean always the noise. This is the part where we're adding noise. Now, here, the first decision tree regressor did not do anything much. It was just trained with the depth of 2, and then we did the predictions using this. We subtracted the actual prediction with the newly predicted values. Now we got this residual error. For the next stage, the decision tree, this is a new decision tree regression. For the next stage, the important part is that for the next stage, the labels are these. Labels are these. Okay, so I hope you got it. Why? Right? So whatever error it made in the first go, those errors becomes the objective for this one. Okay. Now, similarly, we could do one more label, y3. This is y3, and so on. And once we are done, what we do is we ask all of these. So we go over the loop. We say for tree in regressor 1, regressor 2, regressor 3, and we let it predict. And then we basically do the sum. Okay, so this is what I mean, this code might look little strange to you. Let me just make it little better. Okay. So, all right. So this is what's happening. So let's say this is our x underscore new is the instance on which we are testing. These are testing instances. Okay. All right. So what we're doing here is we are saying these are my predictions. Predictions equals, okay, let's say empty. And what we do is for this part, I'll just copy paste it. For this, okay, we are saying predictions dot append. Okay, predictions dot append, we are saying, okay. So we are, from each tree, we are just taking the predictions, right? And then we are saying y predicted value as sum of, okay? So you can see this. So basically these two codes are equivalent, right? In case you are not clear about what it means. All right. In the meantime, let's also try to go over the notebook. Any questions on this so far? This is gradient boosting should be pretty straightforward for you. A question from Robert is, in this list comprehension, it's missing the brackets. I do wonder. So, okay, I think it should be like this way, something on this line, right? This is what you mean, Robert? I'm just wondering, okay, all right, let's just check it out. I'll test it in the notebook. Okay, is everybody in the notebook? Just run the include part. All right, I think rest of the things are going to remain the same. And let's run this also. That's all right. Moving ahead, let's see if we can run it and it doesn't give us an error. So this was the example of the, all right, it wants me to run everything, run all above. Okay, let it execute. It should not take too much time because we don't have too many trainings to be done. I think this is little more. Other than that, I think it's okay. Okay, so looks like we are all covered. All right. Okay, so this is how we plot it with respect to all these values. And okay, so let's just take a look. This is very clear to all, yeah. And then we plot the boundary the way we did earlier. And here, looks like this is some residual part from my previous session. So we're using SVM here, okay. SVM, then fit, predict, and okay. So basically we are running this loop twice and we are trying this 5 times, okay, with the different values of, are we using I anywhere? Okay, so here essentially we're trying to plot this graph with, this one is with learning rate as 1, with learning rate as 0.5. Okay, so that is the case of error boost. All right, now moving ahead. Okay, so you can find out all the classes that end with underscore. and that way you can find out find out which are the which are the methods provided by the AWS classifier, such as once training is done, you can find out the base estimators, and you can find out the classes, the estimator errors, and estimator weights, and also the estimator. So once the training is done, you can use these, you can extract this information from that. That's what we are trying to show here. All right, now let's try the gradient boosting. Here, X and Y. Then we train the first decision tree regressor, then second one, and then third one. Okay, now we got three, right? We got three, we got three recent trees trained on the same data, just that for the second one, the data is a little different, the Y is different. For the third one, the Y is a little bit different, and it's basically how much incremental improvement it has made from the previous one. All right, let's say for 0.3, the ideal answer should be 0.27, and let's take a look and say here, let's say we created capital X, the one that is we want to test as 0.3, and we want to see that if our predictions can be close to 0.27, because this is what we have done, 3x squared is what we are doing, right? Now, here we go. So this is what we are saying, okay? So we are iterating over each of the regressors. We're saying for tree in this, and then we are doing the predictions for all. And then we are summing up the value, and the answer that we're getting is a little different. Instead of 0.27, we are getting 0.17. Okay, the predicted array of each of the regressor was this. First one predicted 0.12, right? Second one predicted this much. This is basically predicting the error from the actual, the error of the previous one. Okay, and third one was even the error on error. Okay, so gradually this is the kind of results that we get, right? Now, okay, let's just try to plot some values. Okay, so you can see that basically the residual entry predictions are on these lines. They keep on kind of getting minimized. The second one operates on first one's errors, and so on, right? Let me try to show you that part. Okay, so I hope this is correct, Robert. All right, I think you can't really this part. The only way I can put it in a single step is by the way of probably like this, right? You could just say sum and so on, right? Only then we can do. Cool. So let's move ahead and yeah. So the ensemble has just one tree. So its predictions are exactly the same as the first prediction. Okay, so this is what we're talking about. We are plotting the predictions. So first we are plotting the predictions of tree regressor 1, tree regressor 2, and tree regressor 3. And here we are basically plotting the predictions of 1 and 2 together, and then all the 3 together. Okay. All right. So, right. So this one is okay. Okay. So you can see that This one has far better results than this one. All right. So the ensemble has just one tree, so the predictions are exactly the same as the first tree's prediction. Okay. So therefore, these two are exactly identical. And then after second step, this is the predictions on error, right? Because this is the error done by the first step, and the second predictor or second class regressor is essentially trying to fit into this. Okay, and then when we sum up this and this, we get this kind of prediction, right? Okay, so I hope this makes sense to you. So initially, this is our decision tree regressor. The ensemble contains only one, therefore these are identical. There's nothing much. The second step, we have like the H2, the second regressor, which is being trained on errors, not on the original data. The Y had changed, X remains same. The Y had changed. Therefore, this was the error in case of this X. This was the error in case of this X, and so on. So these are the residual errors on which we are training this. Now, once we combine this and this, we get this kind of outcome, right? So for this value, we sum up these and these. For this value, we sum up these and this, and so on. So once we get these predictions, this is more closer to the actual data, right? Further, the third regressor is like this. The errors are kind of noise. You see that errors are kind of noise, and it realizes that just a straight line will fit, and not much of a decision is being made here, right? So when it goes further, this is the kind of tree we get. We sum up this and this, then we'll get this, right? So that's what is happening here. And okay, so we are progressively we are incrementally making the progress, and that's what is gradient boosting about. So a simpler way to train the GBRT, gradient boosted regression tree ensemble, is to use scikit-learn's gradient boosting regressor class. Just like random forest regressor class, it has hyperparameters to control the growth of decision trees, like max depth, minimum sample leaf, and so on. Okay, there would be, I'll just show you this part, as well as hyperparameters to control the ensemble training, such as number of estimators. All right, so we can simply say gradient boosting regressor, maximum depth is 2, maximum number of estimators is 3, and learning rate is 1. So we can say that gradient boosted GBRT.fit, and we'll get the results. So this is how it looks like. Right? So number of estimators is what decides how many level we want to go. Probably this one is going to be passed to the next one. Let's also take a look at the manual. We should always get used to looking at the manual. Okay. All right. So here this the least squares regression, and then absolute, and so on. Okay, these are the loss functions. And learning rate, number of estimators. All right, this is interesting. So the fraction of samples to be used for fitting the individual based learners. Okay. If you change this value, it becomes, if you change the subsample, right, every time, instead of improving the entire data set, if you want to improve only the subset of it, random subset, in that case, you can do enable subsample and so on. Okay. And there are quite a few methods over here. Okay, and we'll talk about those as we go ahead. Okay, so the learning rate hyperparameter scales the contribution of each tree. Okay, and there's it provides a way to, if you set it to low values such as 0.1, you will need more trees in the ensemble to fit the training set, but the predictions will usually generalize better. This is a regularization technique called shrinkage, right? So instead of just let the contribution for each of the subsequent trees to be one, the way in our example, the contribution was one, as in whatever value they were predicting, we were just adding them usually, right? We can change that to some fraction, okay? So here the learning rate was 1, and here learning rate was 0.1. Okay, learning rate was 0.1, and we needed a lot of trees in order to fit the training set. Okay, this is, question is, how do we find optimal number of trees? Yes. All right. So a question from Robert is that, wouldn't 0.1 be considered overfitting? Yes, it is overfitting. So how do we control it? We will have to bring down the number of estimators, or let the number of estimators be like this, and we decrease the depth. Okay, make each tree to be more flat. Okay, so we can actually reduce the number of estimators, as well as we can control each one. So this is essentially overfitting. Okay, all right. How to find the optimal number of trees is the question. This one was overfitting, this one was not. This one just was having 3 estimators, and this one was having 200 estimators. And therefore, we need to figure out what are the best ways. Now, there are multiple ways. One of them is called the early stopping. A simple way of implementing this is to use stage predict method. It returns an iterator over the predictions made by the ensemble at each stage of the training. First with one tree, then second, and so on. Right? So what we can do is we can um, stop early. Okay, we can stop early. So let's take a look. The here probably. Okay. Let me just go through these tabs and run it. Okay. All right. So here is an important part. So let's say we define gradient boosting regressor with depth as 2, max number of estimators is 29, and learning rate is 0.2. There is no reason why we have kept it 29. We could keep anything else. Then random. All right. So let's just here learning rate is 0.1 and so on. So here we have done the fit and then predict, and then we are seeing the loss. So this is the loss, right? This is the loss on basically the same training data. And okay, and this loss is essentially the basically mean square error. Okay. So this loss is essentially this. You can see We are subtracting the actual from predicted, then squaring it, then dividing by length, and then summing up. All right. So okay, now moving ahead. So here, let's see what happens here. So what we're doing is we are doing something called stage predict. Okay, so what is stage predict doing here? Basically, it's giving us the iteration at every stage. So we defined a tree, we trained it, and then we are using something called stage predict. Meaning, as it is on every stage, it's adding the estimators. As it is adding the estimators, it's giving us the control. Okay, it's giving us the control, and we can choose whether to stop it or break it. Okay, so instead of it being a black box doing some iterations inside, it can give us the control over this. Okay, it can give us the control over this. Basically, at every stage, we can enumerate over that. It gives us the iterator to it, and we can stop it by doing the break. So as and when the value is being predicted here, right? So initially, let me just show you. Okay. How can I sell output clear? Okay. So here, basically, what we are doing is we are iterating, we are running through the iterations of this gradient boosting. So what it will do is it'll basically try to first use the one estimator, then second, then third, then fourth, and so on. So using stage predict, we get the control or the move. I mean, the number of steps into the into the into the into this what do you say, the into the algorithm. Right now, let's say I increase this to say 50. Okay, so now it has got 50 trees. Okay, and now when I start iterating, it'll basically stop as soon as we reach this error. Okay, if we so what we're doing is at every stage, as it is predicting the next step, we are checking if we are computing the loss, right? Just it's basically root mean square error. And then if this error is lesser than this, we break, otherwise we go ahead. So I've just increased the error and looks like decrease the error. So here I put one more zero. Looks like we are not able to achieve this error even after 50 iterations. Okay, so let's say we are okay with this kind of error, then we stop at 29th. All right, that's how we figure out that okay, these are the number of estimators we need. We don't need to 50, only 30 will be good enough. Okay, based on what kind of accuracy are we looking for? So in the cases we have expectation of accuracy, we can do the early, we can basically do the early stopping. Okay, all right. So this is what is what we are doing here. We basically doing the stage predict, and even here what we can do is we can just take a look at the plot. Okay, as the number of trees are growing, so this iteration that it printed that we just need to go up to 28, that was basically number of trees. Okay, so here as the number of trees are growing, the validation error keeps coming down, but after a point of time it kind of becomes stable and slightly starts increasing. Why? Because it has started overfitting. Okay, so the validation error, you could, if you plot, generally this is the kind of validation error you will get. So first you trained on 20, then 40, then 60, and like that. So as you increase the number of trees for training, the validation error will come down and will reach a minimum, and then it will increase. Now you can see that here instead of saying that let's break at this particular value, if we don't know, what we can do is, in case consecutively we keep track of what was the error previously and what is error now. In case the error has started increasing consecutively, then we can stop then and there. We don't go ahead. All right, that's also another way of looking at early stopping. So early stopping can be done by the way of maybe the minimum error that we're looking for is met, or the error has started increasing, or error has not decreased for last 3 consecutive values. So those kind of strategies we can ourselves come up with. Okay, so the best models predictions are like this. Okay, you can see it has very tiny steps, right? And this looks like the best the gradient boosting could do. So in this case, the best estimator was giving around 55 number of trees. Okay, so it is also possible to implement early stopping by actually stopping training early instead of training a large number of trees first and then looking back to find the optimal number. You can do so by warm start equals true. Okay, so the scikit-learn basically will keep the existing trees, and when the fit method is called, so I think almost every model that we use has a method called in the fit. Every model has a method called fit. In the fit, we can also pass an argument called warm underscore start equals to true, meaning whatever training was there already, do not wash it away, keep it there and do the training from there. Okay, so if you usually call fit, it basically, I think, resets warm equals to warm start equals to false, so it let go of whatever it learned earlier. But if you say warm start equals to true, so it basically incrementally does the it basically incrementally does the work. Okay, so let's take a look at it here. So we are saying gradient boosting regressor, and then we are saying warm start equals to true. Okay, and what we are doing here is we are increasing the number of we have the same number of estimators as 120. Okay, and here we are saying that GBRT dot number of estimators equals this many estimators, and we are saying GBRT dot fit. Since we have said warm start equals to true, so every time we fit, it's going to basically progressively add those many estimators. Okay, and then we can say GBRT.predict and so on. So here the important part to understand is that this error going up flag is what we are tracking. Okay, the moment the error if error going up becomes 5 times, it goes beyond 5 times, that the number of times the error has gone up. If it becomes 5, we break. Okay, so what we are doing here is that we are progressively training the gradient boost first on one estimator, then two, then three, then four, and so on, right? And this one is incrementally learning instead of training everything from the beginning. So, and at every stage, we are figuring out whether the predictions are right or predictions are wrong, or how much error are they making. Okay, and you can see that we are predicting based on the validation set, and the validation error we are computing here using mean squared error. In case the validation error is lesser than minimum validation error, that means we are doing good. That means training is going good. And we are updating our minimum validation error. Minimum validation error is initially infinite. Okay, initially infinite. And then here, every time minimum validation error is keeping the minimum validation error is achieved so far. If at any point of time, the current validation error is greater than or equal to minimum validation error, we are saying that error going up plus equals to true. Okay. And if this happens 5 times, so if error remains same or error goes up, if that happens 5 times, then it breaks. Okay, so this is one strategy of early stopping. You can generally apply or use this kind of strategy, or you can come up with your own strategy that, okay, I don't want 5 times, all I want is just the last 3 times, or the moment the rate of decrease of error has dropped down these many values, let's stop. Okay, so those parts you can do you can experiment and figure out which one is suiting you. Okay, so all right, in case you want to just every time when we are training, you just want to give the subsample to it, you can just say subsample hyperparameter in the constructor of the gradient boosting regressor. Okay, so basically this will give you more bias as compared to the overfit. Okay, this technique is essentially called stochastic gradient boosting, as we saw in the manual, that if you change the subsample parameter, it'll basically how many training instances to use for each tree. So every time it'll just pick randomly some subsample and so on. So that way you will generally get a little better outcome. All right. Now we will start from stacking after the break. Let's take a break for 10 minutes. All right. So far we covered quite a few things, and I hope you're finding these useful. And the next part in case of gradient boosting is called stacking. Stacking is basically an ensemble method. And instead of using the trivial functions such as hard voting or soft voting, you remember the first example that we took, in which all we did was we asked all the classifiers, the various algorithms, to do the prediction. And then once they had done the prediction, what we were doing, we were simply taking the voting, right? Either probabilistically or like just vote counting. Like if you are using probabilistically, that is soft voting, and in case you're using the hard voting, in case you're just counting, that is called the hard voting, right? So either you do the hard voting or soft voting, that is the simple way. Now we could actually train another model to perform the aggregation. Instead of just using summation, we could just figure out that this model seems to work good on such instances. This model seems to work on such instances, and so on. We could train another model which will keep track of how much value to give each one. Okay, so this is called blending, right? So the merging of the predictions of the previous step using another algorithm is called blending. Okay. So for such values, like the blender will figure out that for such values, this one is performing good. For such values, this one is performing good, and so on. So blending is a great technique in the way that we could merge multiple algorithms. Okay. So till this point, we did as part of voting classifier, soft vote or hard vote, right? That we will when there is a new instance, we will let all the models predict, and then we would basically do the summation. But here we are training the blender on the previous predictions. Okay, so each of the bottom three predictors predicted as 3.1, 2.7, and 2.9. Then the final predictor called blender or meta learner takes these predictions as input and make the final predictions. Okay. Now, how do we actually train the blender? Anyone? So if let's say, what will be the input to this predictor, and this predictor, right? Should we just train them with X and Y, the usual data sets? And then the blender, whatever predictions it is doing, for it, the X becomes this and this and this, and then it does the prediction. Will that be good enough? All right. Actually, the answer is no, right? Actually, the answer is no. It won't be able to perform great. I'll tell you why. All right. For each different data set, yeah. Manoj, do you want to write the message, rewrite the message? Take different data set for each. Okay. Okay. All right. So Manoj's suggestion is that we take the different data set for each, maybe different sample for each. Is that what you mean? Good point. Anybody else has a point here? All right. So if you notice, Blender is being trained on the previous steps output, correct? Until these previous steps, until these guys give any output, there is no input to the Blender, right? So these guys, these algorithms need to do prediction before Blender can be trained, right? Therefore, we would require maybe another sample, maybe another part in order to do the blending, correct? Does it make sense? That Blender can only perform the predictions, Blender can be trained on the predictions of the previous step, right? Until the previous step, there are predictions, the Blender cannot do much, right? So the way we do is we break the training set into two parts, subset 1 and subset 2, right? On subset 1, we train the predictors in the first layer, and here the target values remain the same as the actual training set, right? The Y remains same here. And on the subset 2, what we do is we do the predictions, okay? So on the subset 2, on subset 1, we did the training of these predictors. And on subset 2, we let them predict. And whatever predictions we get, this becomes the input data for our what do you call the Blender, right? So first, the training set is split into two subsets, right? The first subset is used to train the predictors, in the first layer. Next, the first layer predictors are used to make predictions on the second set, that we call it held out set. And so we call this one as held out set. Okay, so this ensures that predictions are clean, since predictors never saw these instances. If we could basically did not split it, first we let it train on this and then again predict on this. Here, if it was the same subset as the previous, what would happen is these all errors would be 0, right? And there will be nothing to predict. Therefore, it won't be able to reduce the errors. Now, for each instance in the holdout set, there are 3 predicted values, right? We can create a new training set using these predicted values as input features, which makes this new training set three-dimensional and keep the target values, right? All right. So basically, whatever are the predictions based on the second subset, that becomes the input data to the Blender. The Blender is trained on this new training set, so it learns to predict the target value given the first layer's predictions. Okay, so y hat of each one becomes the input to the Blender. So how many? All right. So how many columns does? Okay, let me ask you this. So for each instance, right, there will be 3 predictions, correct? For capital X, even if it has 100, features, there will be 3 predictions. For this data set that we are feeding to the Blender, how many rows and how many columns will be there? Anyone? The Blender is being trained on what size of the data set? How many columns and how many rows? Yes? Okay. Prashant says 100 rows and 3 columns. 3 columns is right, but are you saying that subset 2 has 100 rows? Okay, very good point. Yes. So the shape of Y is, let's say, 100 by 1, 100 rows and 1. Okay, good point. So let me put the numbers correctly. Okay, imagine that you had total training set as, say, 200 values. Okay, so sub 200 by 1. Okay, sorry. The shape of X is, let's say, 200 by 10, and shape of Y as 200 by 1. Okay, just for this case. So subset 1 would have approximately what size, what shape? 100 by 1, 100 by 10, right? And subset 2 would have 100 by 10, right? Okay, let's call it x1, x2, and so in this case, y1 is going to be how much? $100 by 1, right? That's right. And okay, now let's say input to Blender. Okay, let's call it x3. How much? What will be the size of it? And there are, let's say, there are three in the previous step, there are three, let's call them predictors. Okay, there are three predictors in the previous step. So what is the size of it? Shape of it, not. Okay, shape of it. So it's going to go 100 rows by 3 columns, right? Not clear? So for row 1, right? Predictor 1's prediction, prediction 1, prediction 2, prediction 3, right? That's going to be the instance, right? This is like this, okay? And the y will remain as such. Okay, so it'll be 100 into 3. The y is going to be 100 by 1. All right, that's the only part we need to understand about the stacking. Question from Deepak is, but prediction y cap is same as y shape? Yes, that's right. The shape of y cap and y is going to be same. All right, a question from Robert is, what happens to the lone column? Which column? Okay, that row column I have removed because that doesn't make sense. I was saying row 1, right? That one, I've removed that because that doesn't make any sense, because here these all the three predictors gave their predictions, and they become these predictions become each features. Okay. All right, we have 3 features. If we have 3 predictors, there'll be 3 features. And originally we had 10, that's right. That's right. So for all those 10 features, what will happen? That this 100 by 10 is being fed to this. What's going to give? It's going to give 100 by 1 value, 100 by 1, 100 by 1. That's the y, right? At each stage. And then what we do is we basically concatenate their columns such that the prediction of this is one column, the prediction of this is another, prediction of this is another. And that way we can feed to the next. All right, we assign 3 for each subset. I hope everybody got the clarity on this. Please feel free to ask. Okay, because the dimensions are the very important part, and the dimensions are basically quick way of understanding whether we are doing good or we are doing right or wrong. A number of times, if you see as we go ahead in case of neural networks also, number of times understanding of the dimension is very, very critical. All right, because that generally reflect whether we got it or not. Okay, so it's like the dimensions that used to have like M and L and T, right? Mass, length, and time, and we used to calculate if the dimension of velocity or the speed is same or different, and so on, right? In the same case here, the dimension of the data generally give you the clarity on what's going on. Not always, but generally. Okay. I hope everybody got the idea. All right. So yes, so it's actually possible to train several different blenders this way. Example, linear regressor, another could be random forest regressor, and we get a whole layer of blenders, right? So also notice that the training of individual parts can happen in parallel, but the blender still have to wait until the predictions are done. Okay, so the trick is to further, right? Further, the trick is to split the training set into three subsets. First one to train the first layer, second one to create the training set used to train the second layer, and third one is to create the training set to train the third layer, right? And so on. So you could create more layers and so on, right? Once this is done, we can make predictions for new instance by going through each layer subsequently. All right. Right. We could even have like two layers. And in that case, first layer will be used to, first part, let's say we will have to split the data set into three parts. First part will be used in training here. Second part will give the outcome here and give the input to this. And third one is we are going to run both of them against the third data set, and these will give the predictions, and on that we can train this. So this was the older technique of chaining things together. But when the neural networks came into play, people realized that that is far easier to train than these. Okay, the reason is that if you have like 300 records, suddenly your training data size reduces to 100. Okay, training data size suddenly reduces to 100 and reduces to become like 1/3 of total. So this is, though this may look really great, but at the end, and it actually does a very good job, but at the end, it is able to handle some amount of nonlinearity, but the neural networks have been proven to do a far better job. But this is a good idea to know that there are multiple phases going on. First phase, train this. Second phase, predict using this, train this. Third phase, predict using both of them, and then train this. Okay, and then finally, this model is ready to do the predictions. All right. Now, the next one is a very important algorithm historically. It was created in 2014. It's called XGBoost, Extreme Gradient Boosting. So we talked about AdaBoost, we talked about gradient boosting, we talked about stacking, and before that we talked about the various kinds of classifiers and random forests and so on, like bagging. We talked about bagging, pasting, then we talked about boosting, we talked about AdaBoost, gradient boost, stacking, and now we're going to talk about the XGBoost. All right, so these are various tactics, and the idea is to build a kind of intuition on how does the models work, how do we train them. You can always with all of this understanding and behavior of various algorithms and models, you can actually come up with your own designs, your own models, your own optimization techniques. And most of these techniques have come by the way of experimentation and doing the research and trying to come up with better accuracy and coming up with low underfitting and low overfitting, right? So this one was done in 2014. Okay, it's basically a family of boosting algorithms. That basically most of the boosting algorithms, what they do is they convert a weak learner into strong learners. This XGBoost is optimized distributed gradient boosted library. Unlike the other boosting algorithms, XGBoost is distributable. This is used for supervised learning problems, and it uses gradient boosting framework at the core. And the inception of it was in 2014. And it's a basically, this has been really a big, kind of true love for Kaggle users. But most of it is now basically, again, the neural networks are also doing pretty well. But there are many problems that can be solved with XGBoost better than the other algorithm. So after 2014, for up till probably 2017, right, for last 3 years, XGBoost was a clear winner for most of the competitions. And XGBoost is basically a boosting algorithm and ensembling algorithm, whereby we combine multiple trees in order to create something, right? So I'm going to walk you through this. Also, XGBoost offers many hyperparameters, and by default, it uses the cores. It can use multiple cores of your machine, and there is something called OpenMP that's basically a standard for distribution, right? So other than yarn, the other one that is very well known is OpenMP. It's basically specification or standard for the parallel programming, and there are many implementations of it. Okay, so it basically, any platform which enables OpenMP can it can run on that. It has been exported to Yarn, as in people can run XGBoost on Yarn. Yarn is YARN, that is Hadoop's way of distributing work on the cluster. And XGBoost has regularization. The biggest advantage of XGBoost is that that it has lots of things that we could fine tune. Like remember the question from Robert, that the things that we could tune in gradient boosting were only few, right? There were only few things like number of estimators and eta. Those are the only two things to do the regularization, right? But nothing much, correct? But XGBoost provides you the capability of fine-tuning many things, okay? And it enables cross-validation, right? Internally, it has the internal CV function, okay? And XGBoost is designed to handle missing values internally, okay? So the magic about XGBoost is that in case the values are missing in certain manner, it figures out that pattern also, and it captures that particular model. It's very flexible, can be used for regression, classification, and ranking problems, just like any tree. Supports user-defined objective functions, so you can define, instead of considering the mean square error for everything, you can define your own objective functions. It supports user-defined evaluation metrics. As of today, it's available in almost all languages, and features to save its data metrics and model and reload it later. All right, so let me just check if the current these are all done. All right, you should take a look at this code after this session. You just take a look at the code of this. Let me see if we are able to. All right, so it's pretty simple. All you need to do is say from XGBoost import XGB classifier and fetch ML data and so on, and then you can just train it. It takes some time to train. Right now we are training it on MNIST. All right. All right, let's see how much time it's going to take. Yes, that's right, Deepak. So is XGBoost part of scikit-learn? Good question. It's not part of scikit-learn. You have to install it separately. But it provides scikit-learn friendly API. On the same lines, it provides the API on the same lines as scikit-learn, but it's not part of scikit-learn. Question from Deepak is, does it do feature scaling also internally? Most of the decision trees, they don't require feature scaling, right? Therefore, XGBoost does not really require feature scaling. Good question. Question from Deepak is, to what extent do we need to do data cleaning and preparation ourselves, and what XGBoost does? So the conversion from the categorical variable to numeric variable is one thing that you need to do. And the remaining part, like filling in the missing values, you can do using any method. Even if you don't do it, it's okay with that. And all right. And the other part is scaling. Scaling is not much required. Okay, it takes care of the filling value, missing values, it can take care of the scaling and so on. So the only part you need to take care of is converting the categorical variables into the numeric variables. All right, now it has done the training and we can take a look at, so we just did XGB classifier and here there is a random classifier, random forest. We are training both and we're just printing the accuracy of all the three. So what do you see here? Do you notice the difference? So there is stochastic gradient descent, there is random forest, and there is XGBoost, right? So here we created a random forest, we created a HGD classifier, and we are predicting on the same test data from MNIST, right? So what do you see? Which one is performing the best? All right. So though XGBoost took some time to train more than random forest and SGD, it took some time to train, but it did a very good job. All right. And we could basically do the grid search over so many hyperparameters that we have. And there you can take a look at, there you can fine-tune further the XGBoost in order to improve its performance a little bit more. Okay, so right now it's giving us 91.36 accuracy. You can actually push it to maybe 93 or so. So this was the XGBoost, and do you want to go through what exactly does XGBoost does? What is the magic inside it? Deepak, Narayan, Manoj, Nikita, Prashant, Robert, Robin, Satyajit. Do you want to go? Do you want to understand how does it work? All right. So I'm going to walk through their own tutorials. Probably. All right. And this tutorial is actually wonderful. It's actually really well written. There are some parts that may not be very clear to you. So I'll just walk you through this tutorial. Probably you can spend some time understanding what it is. So I'll just take the author of XGBoost, Tianqi Chen, his talk at University of Washington, right? So, and the good part about this presentation is it kind of refreshes the entire idea about the machine learning in general. Okay, so I really like that this presentation. Okay, so I think I'll just walk you through. Let me just download it. Probably that will be a better idea. Okay, let me just try. Okay, let me just open it in the preview. All right. I'm going to, it might be a little mathematical. Don't worry. It's not such a big deal. You can figure it out. All right. So I'm going to just explain wherever you get stuck. Okay. All right. So basically okay. So these are notations that we have already learned, that the xi is the ith training example and so on. So this is x means instances. And the way we do the predictions is we call it y cap. And the way we do the predictions on linear model is basically come up with these w's so that we can multiply with xi and sum them up, and we get this model, right? The prediction score can have different interpretations. It could be a linear regression, whereby we are getting the actual value. It could be the classification, in which case we will use the logistic regression, and we will basically come up with this probability, right? And so on. So this prediction score could have different values, right? The parameters is something that the things that we need to learn from the data, and this is called the model, right? I hope everybody is so far clear about it. Now, the important part, we are cutting short the entire journey. It will be a quick review of entire thing. So the objective in case of machine learning is to minimize the training loss and minimize the overfitting, right? Minimize the training loss and minimize the overfitting. Thetas are this theta that you see, basically that is the model, and this loss is a function of model, and the regularization is also a function of model, right? So if imagine that in case of normal linear regression, on one hand we try to come up with lots of thetas with their values, right, such as we can minimize the loss. But at the same time we penalize by adding a regularization term by ridge, or what was the other one? Ridge regression, and what was the other one? Anybody remembers? What was the regularization term in case of linear regression? Oh, you forgot. All right. There was elastic net, right? There was ridge, and there was third one that is missing. All right. Lasso. Here it is. All right. So this, I hope everybody is okay with this so far, right? We've used these terms over and over again. There's only a slight bit of difference in the symbols. So the objective function is basically the loss function, the loss on the training, and this one is loss due to, as in the regularization term, basically measuring what kind of errors we are going to make due to overfitting. Okay, that's what we want to minimize. Therefore, we want to bring in the regularization, and in case of the linear model, we either use the L1 or L2. We either use the sum of all the weights, absolute sum of all the weights, or we use the square of the sum of the weights, right? So
And the loss function is in case of the normal training linear regression, the loss function is like this: y1 minus y dash square and so on, right? This has been our loss function probably for everything. This is for this loss function was our loss function in case of regression, and this one was in case of classification, the logistic loss. All right, so everybody okay till this slide? Right, it's kind of quick recap of the machine learning. That's another reason why I wanted to walk you through this. Now, if we do ridge regression, the objective function turns out to be this. Question from Manoj is y1 minus y cap. What is the second y1 over there? You mean this one, right? Y cap is so this is the actual value. This is the predicted value, right? So what we are doing is we are subtracting actual label from the predicted and then squaring it. That becomes our squared loss, right? All right, now if our regularization term is like this, square one, we call it ridge. If it is mod, the absolute value, then we call it lasso. And in case of logistic regression, this is how the equation looks like. You see this, right? Here, basically comparing actual class versus the predicted class. That here when we are comparing actual class versus predicted class, the probabilities, this is the kind of formula people use because they want the loss function to account for this should be loss function should be minimum when both the classes predicted and actual probabilities are same. If they are different, this loss function has to be huge. Okay, so the idea is to come up with a loss function such as the predicted class and the actual class are having the similar probabilities. Okay, so this is the idea. So here the important part that we should notice is the L1 and L2 regularization. Okay, the conceptual separation between model, parameters, and objectives gives you the engineering benefits. So there is model, there are parameters, and there is an objective function. I hope we are all clear about these three, right? Think of how you can implement SGD for both ridge and logistic regression, right? So SGD being really generic algorithm, no matter whether you are using the objective function as logistic regression or you're using the ridge regression, it doesn't matter. The algorithm remains same. The only thing that you need to plug and play is the plug and retry is you can have model could be your SGD, the parameters would be different based on the model, and the objective function could be anything else, right? You can have SGD with what do you say that what was that in case of SVM, what was the objective function? There was a term that we used. So we could have SGD. We could have SGD doing the. We could have SGD doing the SVM, having the SVM objective function, and so on. This is the important part. Now, again, get back to the point that why do we want to contain two components in an objective? Optimizing training loss encourages predictive models, fitting well in training data at least at least get you close to the training data, which is hopefully close to the underlying distribution, right? So when we are optimizing the training loss, what is it that we are trying to do? We're coming with some model which is very close to the actual values, right? And actual training values, the training data. And we are hoping that the training data is very similar to the testing data and the underlying distribution, right? So while the regularization encourages simpler models, we force a complex model to become really simple by the way of by the way of regularization. Simpler models tend to have smaller variance in future predictions, making predictions stable. Okay, so that was the quick review of the concept. So idea is, while our objective is the core objective is to come up with a model which actually does real predictions. Okay, so we start with minimizing the loss and hope that whatever function we come up with is very much closer to the real, right? And but while we are doing so, we end up with complex models, and the regularization term helps us making the complex models simple. Okay, so regression tree and ensemble, that's what we're going to do, right? So while we were discussing the card, the regression tree, also known as classification and regression tree, the decision rules are same as in decision tree. Contains one score in each leaf value. Now you can understand that the XGBoost part basically builds up upon whatever we have learned so far, right? So so what we do is, given, let's say we are given some kind of data, and we are trying to, whether the age, the gender, and so on, or occupation. Based on that, let's say we are trying to come up with certain prediction that maybe, does a person really like the computer games, right? So we come up with these boundaries as part of CART, this algorithm that we use. So we try all possible combinations, and we figure out that, okay, that the age less than 15 is one such criteria based on which we can divide the sets into two parts, such that the people on the right and the people on the left will be similar to each other. Okay, most similar to each other. A question from Deepak is, does XGBoost use CART? We'll see that. Okay. Okay, it's a slight variance of CART. All right. Now, the next thing we check is on the right-hand side, we do that same thing again. We try to split it again and again. And here we see that, okay, one of the criteria it has figured out is that the gender being male. Okay, if the gender is male, then the prediction score in each leaf is +2. Okay, and so on. Now, what's happening here is that we are coming up with a model. We're coming up with these conditions such that we can predict whether a person likes the computer games. And based on the historic data, we created this tree, which tells us, we created this tree which behaves like a mental model, right? Okay, and based on each leaf, we mark that how much the person likes the computer games. Okay, and so on, right? Based on existing values. Right? I hope everybody is okay with so far. So imagine that we have two trees, okay? Tree 1 and tree 2. We created these two trees based on maybe some other random factors. So first tree says that, okay, if age is 15 and is a male, then the chance of playing the game is +2. If age is greater than 15, the chance of playing the computer games is -1. If the gender is male, if gender is not male, the chance is lower, okay, and so on. The second one, criteria may be on some other feature, which the tree one did not consider, is that whether they use computers daily or not, right? So if yes, then plus 0.9 and so on. Now, this tree says that this person should play the game 2.9, right? And how we fit in this particular instance into this tree, it says 2, and then we fit this instance into the second one, it says 0.9. That's what we do in case of any other boosting or any other technique, right? And then we get the probability of a person, of a boy a boy who uses the computer daily as 2.9. Now, in case of this old man, he is bigger than 15-year-old. Therefore, its probability as per the first model is -1. And as per the second model, its probability is -0.9. Therefore, the probability of old man who doesn't use the computer daily is -1.9. Okay, if he's using computers daily, chances are that he would fit in here. Okay, if there is an old man who uses the computer daily, then the chance would be -0.1, right? So that's how the ensemble of trees work, and that's what we have learned so far, that we could combine multiple trees to give us great results, right? So when we saw that model, there are many such trees built inside it, like random forest has many such trees and so on. All right, so before XGBoost, most of the models were based on either gradient boosting or random forest, and most of the data mining competitions were won by some variants of the tree ensemble methods. Okay, so tree methods are invariant to scaling of the input, so you don't need to do careful normalization, and you don't need to, they can learn higher order interaction between the features, can be scalable, and are used in industry. That's what we just learned. And if we are putting into the context of models and parameters, assume that we have k trees, right? If we have k number of trees, and if each of the tree we consider like a regression tree, right? If f is our regression tree, we will feed the instance and it will give us the probability, right? And then we sum it up. That's what we did just now. So this kind of function would represent that this kind of function would represent that we are basically doing the prediction from the ensemble. Okay, this kind of formulation represents that we are doing the prediction using the ensemble. Okay, so you can think of regression tree as a function that maps attributes to the scores, right? Including the structure of the tree and score in the leaf. The parameters of the tree, what are parameters in the tree? When you think of a tree, what are the things? First, the structure of each tree, meaning what are the criteria on which we are splitting the tree, and the number of values in each of the leaves. Okay, those are number of value, this is the value, and the structure of the tree. These are the two parameters. That's the model. Okay, that is the model. Or simply use a function as parameters. Okay, f1, f2, and fk. If there are many such trees, then we'll have the structure of each tree and the score of each leaf as f1 and so on. So Okay, instead learning weights in RD, we are learning functions. So like in regression, the way we learn weights, in case of regression, what do we figure out? We figure out the weights. And in case of the decision trees, we are learning the structure of the tree and the value in the leaves. Those are the two things that we are learning as part of in case of the decision tree ensembles. Now, question is, how can we learn functions, right? How can we learn functions? So the idea was very simple, and we have done it over and over again. They define objective, loss and regularization, and optimize it. Okay, consider regression tree on a single input time t. I want to predict whether I like romantic music at the time or not. Okay, so let's say this is the time t. This is the timeline t. And here I met my girlfriend, and the amount of music I liked was yes, and at the time from here to here, the music likelihood was from this to this, and then after a point of time, the interest in the love songs went down. Okay, so right, so you can see that before meeting the girlfriend, when I was with the girlfriend, and after certain time, right, probably a year. So basically I want to predict whether I like the romantic music at time t or not. Okay, if you plot it on the graph, this is how it will look, and we will draw these lines, while in case of model, the tree looks like this. All right, so things we need to learn is the splitting positions at the position we are splitting it, right? The objective for the single variable linear regression tree, how will the function fit the points? Okay, so all right, I hope everybody is comfortable so far that we are trying to predict, let's say, my love for love songs over the timeline. So objective for the single variable regression tree, the step functions, there are two parts. One is we want to bring down the training loss, and second, we want to regularize, right? We want to bring down the overfitting. How will the functions fit the points? That is the first point. Second, how to define the complexity of this function, number of splits. So one thing could be that we could actually come up with multiple kinds of functions whereby the training loss is minimum, right? We could come up with many functions where the training loss is minimum. Say, for example, here we basically kept on breaking it, splitting it into so many parts. This one is, though it might give you great training loss, right? Minimum training loss, it'll give you minimum training loss, but the loss, but it will not be really a simpler model. The objective is to come up with simpler model, okay? And in case we basically don't do too many splits, but we do single split, but at the wrong place, then also the training loss is going to be minimum. In this case, the training loss is higher. In this case, the regularization loss is higher, right? So there are two parts to the objective: training loss and regularization. Okay, that's the trade-off that we all the time do. The entire machine learning, deep learning, or any kind of learning, even in case of human, the idea is to bring down both the functions, right? Not too much memorization, right? Not too much memorization. The idea is to think simple, and also being able to have the minimum amount of loss, right? So simpler is not too much overfitting. That's right, Manoj. Generally, it has been found that the simpler models have less overfitting. Okay. So too much loss, too much regularization, and too less regularization. And here is the perfect balance. Okay. Here is the perfect balance that we figured out that this particular boundary seems to give us a small amount of loss as well as a small amount of regularization loss, right? Is everybody okay so far? Please feel free to let me know. I'm thinking that I'm recapping entire thing. Okay. All right. And also it's important to take a look at the others presentation also, just to make sure that we are in the right direction. We don't overfit too much. Okay. Now, moving ahead, assuming that we have k number of trees, on one hand, if each tree is this function f, right? If each tree is this function f, the predictions, the predictions from each of these trees is going to be summed up, and that will be our overall prediction, right? While the objective is to minimize this loss in the prediction. Objective is to minimize this loss in the prediction. Okay. The other objective is to bring down the complexity of trees, not too many leaves, not too much of height, and so on and so forth, right? So that is the sole idea behind the optimization or training of the tree. A question from Manoj is, why only linear? Most probably it would be curved graph in this case. But in case of decision trees, the boundaries are kind of splits, right? So you always get like staircase instead of a graph, right? In case of decision trees, the boundaries are like a staircase. Right? Like this one. Let's split on this feature, then split this feature, that feature. And also note that visually right now we're only talking about one feature. In reality, there could be like 100 features in 100 dimensions. So we can't really visualize that part. All right. Question from Manoj. So regression graphs, which we studied in initial classes, would be better way of solving that kind of problem. That's correct. That's correct. So the linear regression could do a very good job. Let's say if the data is like this. Okay. If the data is like this, right? If the data is like, this is one point, this is another point, this is another one. So in case of regression, we could just fit a simple line. But in case of the decision trees, it is going to be more like a staircase, right? So you can see the model is complex. All right. But if the data is something like this, the data is something like this. Right? Then decent trees can do a very decent job. First, draw a line and so on. Okay, while the linear regression can never fit it. The decision trees could still come up with some form of outcome. Here, the error of linear regression is going to be too high. Okay, it's a very important question that people ask in the interviews, that can decision trees handle non-linearity? Okay. All right. So this is our objective function, whereby first one is the loss due to error on the training data, right? Second part is the complexity of the tree. This is the regularization term, and we are summing up the complexity of all the trees, right? If we have k number of trees, we are summing up the complexity of each tree. Here, what we are doing is we are summing up the error due to each of the instance, due to each of the predictions of the instance. And this is notice this summation. This one is over n, that is actually this should have been m. So this is okay, let me just think. Why is it n? So training loss, okay, yeah. So n is total number of leaves, probably. Here n is total number of leaves. Whenever we are doing the predictions, not total number of leaves, training loss is, let's say, given the instance, and n is the number of instance actually. N is the number of instance, and k is the complexity, k is the number of trees, and so on. N is the number of instances as per my understanding. Let's just go back. Has he defined what it means? Okay, I think he is using n. Yeah, he's using n as a number of instances, not the features. Okay, so that is a little difference from our terminology. Okay, n is the number of instances, and so it's computing the error on each instance and finding out the training loss, then computing this part. Meaning, as you increase the trees, please notice this, as you increase the trees here, what will happen to the error, the loss, overall loss, the objective? The loss will decrease or increase. If you add one more tree, what will happen to, if you just add one more tree, what will happen to this part, the regularization part, the complexity of the tree? Will it go up or down? If we add one more, it will increase. That's right, because k will increase, right? And that's right. Now, the possible ways of defining sigma in case of this sigma, or right, this is sigma only, right? Or do we call it something else? It's like ohm, but right. So omega, yeah, thank you. So possible ways to define the regularization term is number of nodes in the tree. Okay, remember that we minimize the number of leaves or max depth and so on. And second is the L2 norms in the leaf weights, just like linear regression. We could do that, right? And we could, right? There could be many more things in each tree that could be minimized. Okay. Right? So when you talk about distant trees, it is usually heuristics split by information gain, prune the tree, maximum depth, and smooth the leaves values, right? Leaf values. So basically, when we were going through the distant tree algorithm, we were splitting by information gain. And we also learned that there is an idea called pruning the tree, meaning that in case it's too much of over regularization, we could merge the two nodes, or we could delete some of the nodes in order to decrease the depth or delete a particular node. And maximum depth is another way of regularizing. Smooth the leaf values, meaning we will basically all right, smooth the leaf values, as in the leaf values under a particular node should have similar values in general. Now, basically find the average of leaf values. Find the average. So this is what we generally talk about. And most heuristics maps well to objectives. taking the formal objective view, taking the formal objective view lets us know what we are learning. Okay, so information gain is what? The training loss will be low. Okay, pruning means regularization by deleting the nodes. The max depth constrains the function space, meaning it doesn't let you go beyond a certain point. And smoothing leaf values as in we could apply the regularization on leaf weights, right? We could force it to keep the leaf values low, just like we did in case of the linear regression. Okay, so regression tree ensemble defines how you make the prediction score. It can be used for classification, regression, and ranking, right? It all depends on how you define the objective function. So far, we have the loss function like y minus y cap square, and logistic function is this, right? We call it logit. Okay, now, so the sole idea is, so far what we learned is that bias versus trade-off, variance trade-off is everywhere. Loss plus regularization objective pattern applies to regression trees learning, not only the other methods, but everywhere. Okay, we want predictive and simple learn functions. We want functions that can predict well as they are simple, right? That's what we want. This defines what we want to learn, the objective in the model, and how do we learn. Let's take a look. So far, we learned that the objective function was this. Okay, everybody is clear about this, probably. Yeah. Now the real algorithm starts. Okay, it's actually simpler. It's not too hard. Okay, I'll explain in case something is not clear. Okay, is everybody okay with the objective function so far? All right, now this kind of method, such as we discussed earlier when we were talking, when Deepak was asking a question related to gradient descent, that we cannot apply the gradient descent to find these functions. We can't really apply the gradient because they're trees instead of numeric vectors. We can't really differentiate it, right? So what we do is we start from a constant prediction, adding a new function at a time. Initially, since when there was no tree, the prediction was almost zero, right? Like in case of decision tree, we split the node, we add another node, and so on, right? In case of XGBoost, what we do is initially, let's say there's no node initially, so the prediction is initially zero. Then, okay, the prediction of when we add one more tree to the whole of the model, or you can say one more leaf we add, or one more. Each tree is essentially I split, if you think about it. Okay, so we basically are adding this. So what is going on here? We are saying that, and we are adding a new function at a time. So this is called additive training or boosting. We start from zero. We add a new function every time we added a tree. Now the prediction became this, okay, which is equal to yi0 plus f1 xi, meaning the prediction at the 0th step plus the prediction at first step. Now, as we add more prediction, like prediction at the second step will be equal to prediction in the first step plus prediction in the second step, right? So this is basically additive training. So prediction at tth step, when we have added the tth model, right? When we have added the tth model, so the prediction is going to be from 1 to t, 1 to t, add the predictions of all of the models, right? As we did in case of these two. Okay, like here. We have tree 1 and tree 2. The prediction from tree 2 is 0.9, right? Prediction from tree 2 is 0.9. Prediction from tree 2 is minus 0.9 in this case. So we basically keep on coming up with more and more trees one step at a time, right? So the model at round t is equal to summation of all the values predicted by each of the tree. Summation of all the values from 1 to t. If there are t trees, the predictions will be summation of all the predictions by each tree. Okay, so the y hat t is going to be y hat t minus prediction before the new tree. Before the new tree was added, what was the prediction, and after the new tree has been added. Okay, is everybody okay with this? Please feel free to let me know. So now the important part is that as we are doing the additive training, how do we figure out which function to add? There could be many functions to add, right? So we optimize the objective. So at prediction round t, at the prediction at round t is basically whatever prediction we were making at the previous step plus this, right? Now the loss function at this prediction round t, because of adding one more function, we have brought down the loss. And how much loss did we bring down? How much loss did we bring down? The loss, if had it been the square value, the let's say mean square value, we'll subtract this from this and square it, and that would be the loss that we have brought down, right? So at any point t, the overall loss is going to be, right? Overall loss is going to be the loss in the previous step plus the loss due to now. Okay, so you can see that the loss at time t is loss of y and yt, comparing the actual with predicted, and the regularization term. This is the regularization term. So this one can be expressed as loss because of the previous step, plus this bracket is going to be here. This is wrong here. This bracket is supposed to be somewhere here. Okay, so here the loss is no, it's actually right. So now the new prediction is what? Yt, and yt is what? Yt minus 1 plus the prediction due to new tree. So this compared with actual value is what is the loss, right? So this is what the loss is. Now moving ahead, so let's say, right, so now considering the squared loss, for now let's just consider the square loss. We'll talk about the Taylor series later. So this loss function is going to be this minus the second value and the square of it, this minus the second value and the square of it, and the summation of all such nodes. This n is number of instances, or is it going to be, okay, we'll see that. Okay, it's going to be the number of leaves also. Now this is the regularization term and this is that. Now here please notice that when we square it, y1 square minus y2 square plus ft square, right? It's going to, and plus 2y minus y1 and so on, right? So there you will notice that we can formulate it in this way, right? We could formulate it in this way. Notice that y hat square we have removed entirely from the equation because, okay, ft square, okay, and let's say we put the bracket here, we say 2 into y. Yeah, we have removed this loss
Okay, y minus y dash t, the square of it. Yeah, I think we have, yeah. Okay, so probably this loss would have been smaller. Therefore, one square term has gone missing from here. Y minus y hat square. Okay. All right, never mind. So moving ahead. So this is our, what has happened here is that if there was a square loss, we will square it and we'll get this kind of value, right? Now, this is our function that needs to be optimized. Right now we have this objective function. We need to find out those FTs, those trees for which this objective function is minimum. Okay, so the goal is to minimize this. Again, we are back here. This was an example in case if this loss was squared loss. Ideally, we should just think of squared loss before understanding the whole thing. So this is our expression. This is our expression. We are saying that when you compare the actual value with the predicted at t step, predicted as t step, whatever is the loss, okay, and combined with the regularization term, that is the overall objective. We need to bring it down to some value. Now there is some kind of Taylor expression which says that if you increase the x a little bit, right, you can predict the value of a function after increasing x a little bit by the way of this formula. Okay, by the way of fx plus first derivative multiplied by delta x and so on, right? I mean, if you just think of all the terms still here, okay, the f dash x is equal to this first derivative, right? That's how we generally calculate the derivative. So basically, there's a Taylor expansion which helps us figuring out the next value of a function based on the previous value by the way of this expansion. But don't worry about it; it's not going to be used much. Okay. Always, if you just think of a squared loss, you will be able to solve it, right? So you don't, this Taylor expansion kind of is digression. If I have to create this presentation again, I'll not use the Taylor expansion at first. Okay, if you're uncomfortable with this, think of squared loss. He has written here already. Okay, so basically what is it that we have this objective function here, whereby right, whereby we haven't actually done much so far. We have just said the same thing over and over again. And here we are saying that we could use the Taylor expansion to figure out the next value. And if we are not comfortable, we can just simply use the squared loss. Okay, and the new goal becomes this. If you consider the Taylor expansion, this is what we get. Sigma of gi, and this gi is like this. Okay, this is the first derivative and so on. Now, and hi is this. So basically, this is a kind of function that we get, right? After we have expanded using the Taylor series, this part. Okay, so here, if we define this gi and hi, the loss of yi, since we are computing the loss of this on next value is equal to loss on this previous value, right? Plus first derivative of this function and plus some value and then second derivative, right? That's what is this. So you can think of in case of gi, it is basically, if you think about mean square error, then the life becomes really simple. Okay, so this is the kind of function that looks to us at every point. So these are 1 to n, and this is the regularization term. So we are spending much we have spent some time to derive objective function, and so we understand what we are trying to converge, and we are also having the engineering benefit. Now moving ahead. Now what's happening is, as we are adding more and more leaf, okay, let's redefine the definition of tree. We define the tree by a vector of scores in the leaf and a leaf index.
right? So at every point of time, we here basically the complexity of a tree is a function of number of leaf does it have. This is the number of leaf and number of weights in the leaves, right? So leaf scores, whatever the scores are there, if those scores are really high, we basically put a normalization term. Now, so we calculated the first term, the objective function, the training loss, and second loss is due to the leaves. Okay. Now, here the objective function is basically going from 1 to n, and this was our earlier the objective function, the way we had written it, and this. Now we are replacing the sigma, the omega, with the number of leaves plus the weights. This is the regularization term that we just discussed, right? That if a tree has more number of leaves, then the regularization is going to be higher. So we have to minimize the number of leaves as well as we have to minimize the weights, right? Now this is what the omega is, and we have got the first term. Now we can reorganize this. We can reorganize this such that we go from 1 to t. T is the number of leaves, okay? Number of leaves. And how can we reorganize that? By the way of counting the, because instances are going to anyway end up in all the leaves, right? In case of tree, all the instances are going to end up in the leaves, correct? So 1 to n, all the values are anyway going to end up in the leaves. So we can here reorganize this structure such that the values here are per leaf. Okay, the values here are per leaf. So overall equation here changes to 1 to t, and here we are summing up the values for each leaf. Okay, each leaf, again each leaf, and so on. Okay, so this way we can reorganize this. This is a very important step whereby we are reorganizing the tree. Now once we get this objective function, what we are doing is we are differentiating this objective function with respect to here we are differentiating this function with respect to the number of t. Okay, so we are going to differentiate this with respect to the t, right? And how does that work is that the way, if you have this kind of equation and if you differentiate it and bring it to 0, then you will come up with the idea that the case where it is going to be minimum is this. Okay, is basically, you can figure it out that the minimum value of x for which this is this is minimum is g plus hx equals 0, and x comes out to be minus g by h. Okay, that's what is happening here. So what we did was we differentiated this and equated to 0, differentiated with respect to t, and we figured out that the case where the objective function is going to be minimum is for the weights at every leaf, going to be equal to this. Okay, and so the final objective function comes out to be like this. Okay, so final objective function comes out to be something like this. So we have this optimization step whereby what we do is we express the entire objective function in terms of leaf, like per leaf, and then what we do is we differentiate this objective function with respect to the number of leaves. Meaning what's happening actually is that as we are adding the number of leaves, on one hand the training loss is going down, on the other hand the regularization loss is going up, right? Because number of trees play a very crucial role, right? So we have to, what here has been done is we have differentiated the objective with respect to t and figure out that value of t for which we can achieve the minimum objective. And that's what has happened here. All right. And once that is done, the final objective is this. Okay. I would suggest you that instead of thinking about a Taylor series, try doing this using the mean square error, and you will get the answer. So the idea is that whenever we are adding a node to an existing tree or a list of nodes to trees, what we have to measure is this objective function, right? We have to see that whether this objective function is being met or not. So for each of the nodes, what we do is we compute G1 and H1. And how do you compute the G1 and H1? By the way of the definition we did earlier. Okay, so we basically at every step we compute the capital I, G, and H, and then compute the objective function, and that helps us. All right, so I think we are already 10 minutes beyond. Okay, so the idea is that whenever we are adding set of leaves to existing nodes, we basically add only the leaves that are improving the information gain, and that's what is being done here. Okay, just like any other optimization problem, if something is increasing one part and decreasing another part, we differentiate and equate it to 0, and we get some results, right? And that's what has been done here. And though there is an iteration involved here, but a lot of part is optimized because of coming up with the formula. So we basically find the best tree structure and use optimal leaf weight and so on. So there still can be infinite possible tree structures, right? So we, at every point of time when we are computing, whenever we are figuring out whether to add a leaf to the node or not, what we do is we basically figure out how much gain are we getting. Okay, how much gain are we getting? The gain due to the left, gain due to the right, and the overall gain, right? If we did not split. Before splitting, what was the gain? Gain due to the left, gain due to the right, and so on. Okay, so that's about this. All right, now we can probably continue from here. Though we have covered a good deal about this, we will continue from here in the next session. I hope you are not intimidated. I hope this idea is clear to you. Just probably this Taylor series expansion would be a little harder, right? All right. So we'll continue from here in the next session. So have a great day. Bye-bye.